Solar panels dominate residential energy, but a spiral design first used aboard an ancient Greek warship over 2,300 years ago has been reinvented as a wind turbine that starts generating power at just 5.6 miles per hour and survived typhoon force gusts. Paired with solar in Seoul, it pushed one home to 92% energy self-sufficiency. The engineering works, the market doesn't. And that contradiction starts with the spiral itself. In the 3rd century BCE, the Greek mathematician Archimedes developed a device that would shape centuries of engineering: the Archimedes screw. Classical texts, including Vitruvius' treatise De Architectura and Diodorus Siculus's historical accounts, describe a helical cylinder designed to lift water efficiently from one level to another. The geometry, an outer cylinder with a continuous spiral inside, was precise enough for Vitruvius to prescribe measurements for optimal performance, and detailed illustrations have survived in Roman manuscripts. Archaeological discoveries back these accounts. The massive ship Syracusia, constructed for King Hero II of Syracuse around 240 BCE, was equipped with a meter-scale screw pump, allowing a single operator to remove bilge water from the hull. In the Roman mines of Rio Tinto in Spain, excavations have uncovered large wooden screws with helical blades, mounted in timber cylinders, used to drain deep shafts. These finds confirm that the spiral design was not only a theoretical concept, but a practical solution scaled for some of the largest engineering projects of the ancient world. Marinus Miramet, a Dutch engineer, approached the ancient spiral from a new angle in 2003. Instead of using the screw to move water, he wondered what would happen if moving air could turn the spiral itself, transforming a pump into a rotor. This conceptual inversion became the foundation for a new class of wind turbines. By 2006, Miramet had filed a U.S. patent number 6,741,000B2 that detailed a helical rotor equipped with permanent magnets and a surrounding stationary stator. The patent assigned to the Archimedes Limited outlined a design that could be scaled from small residential units to larger generators. Miramet's company secured additional filings in Europe and Korea, but focused production efforts through a licensing agreement with K-Wintech in South Korea. In 2016, the first commercial batch of Liam F1 turbines rolled out of Sungjin Precision Machinery's factory in Incheon. Production records confirm that 150 rotor cores and 120 complete kits were assembled that year, destined for small hydropower sites and pilot wind projects in Asia. Despite this technical and commercial progress, the design remained a rarity in Western markets, setting the stage for a deeper look at why the promise of the Archimedes spiral has yet to translate into widespread adoption. Small, 3-blade wind turbines, often called horizontal axis micro-turbines, face steep challenges when installed on residential rooftops. The first hurdle is the cut-in speed, or the minimum wind required to start generating power. Most models need at least 9 to 11 miles per hour, but typical rooftop winds in suburban neighborhoods often fall short. Even when wind picks up, it rarely blows steadily. Urban rooftops sit inside the atmospheric boundary layer, where buildings and trees break up airflow, turning it turbulent and unpredictable. This turbulence forces the turbine to yaw or swivel, constantly to face shifting winds. Every change in direction wears down the yaw motor and bearings, accelerating mechanical fatigue. Studies of rooftop installations report a 30% higher rate of bearing and gearbox failures compared to turbines mounted on open towers. Noise is another persistent problem. The tips of conventional blades slice through the air at high speed, generating a sharp, repetitive sound that can exceed 65 decibels, louder than a normal conversation, and a frequent source of neighbor complaints. Vibrations from these unsteady loads transmit through mounting brackets, further reducing the service life of both the turbine and the roof itself. With high cut-in thresholds, rapid wear from turbulence, and noise concerns, conventional micro-turbines struggle to deliver reliable, long-term energy for homes. The spiral geometry at the heart of the Liam F1 turbine does more than just look different from traditional blades. Its conical helix, inspired by the classical Archimedes screw, is engineered to redirect wind flow through a continuous spiral path. This internal redirection means that instead of relying on sharp blade tips to cut through the air, the turbine channels wind along the spiral surface, spreading force across a broad area. The result is a dramatic reduction in the minimum wind speed required to begin generating power. Where most small wind turbines need at least 9 to 11 miles per hour to overcome friction and inertia, the Liam F1 begins to turn and produce electricity at just 5.6 miles per hour. This low cut-in threshold is possible because the spiral acts as a mechanical amplifier, capturing and redirecting even gentle, turbulent gusts that would otherwise slip past conventional blades. The geometry also helps the rotor self-align with shifting wind directions, reducing the need for complex yaw motors and minimizing mechanical wear. By lowering the activation barrier and adapting to variable rooftop winds, the conical spiral design addresses the fundamental challenges that have limited rooftop wind for decades. Subscribe for more evidence-driven investigations into overlooked technology. On South Korea's exposed Incheon coastline, the Pusan National University research team subjected the Liam F1 turbine to some of the most punishing wind conditions in the region. The site, chosen for its direct exposure to typhoon landfalls, allowed engineers to test both the structural resilience and acoustic low-noise profile of the spiral rotor under real-world stress. Instrumentation recorded the turbine surviving gusts up to 55 meters per second. Those conditions are equivalent to a Category 3 hurricane, and the turbine suffered no permanent deformation. During controlled high-wind simulations, the only mechanical response was a brief, self-correcting stall at the blade tips, with the spiral resuming normal operation within seconds after the gusts subsided. Over a full year of operation, the turbine achieved a capacity factor of 28%, with rated power output reached at a wind speed of 12 meters per second. Acoustic monitoring placed the sound pressure level at just 42 decibels A-weighted, a level comparable to a quiet library and far below conventional micro-turbines. The field data confirmed that the spiral design not only withstands extreme coastal storms but also delivers on its low-noise promise, even under maximum load. Subscribe for more evidence-driven investigations into overlooked technology. Concerns about wildlife impacts have long shadowed wind energy, especially on coastal migration routes. To address this, a Dutch research consortium ran multi-year field trials along the North Sea, deploying 3 large Archimedes turbines near established bird monitoring stations. Weekly carcass searches, paired with around-the-clock video and thermal imaging, produced a clear data set. Over 4 years, just 12 bird strikes were recorded across all turbines, out of tens of thousands of observed bird passages. This translates to a 0.3% strike rate, well below the European Union's 1% threshold for wind installations. In 2022, researchers introduced ultraviolet reflective coatings to the spiral's outer edge on half the units. The mitigation worked, cutting the already low strike rate by 40%. Bat activity was also monitored, with acoustic detectors and direct observation confirming no fatalities and no evidence of avoidance behavior. With a measured capacity factor of 22%, the turbines delivered steady power while keeping ecological risk minimal. The Dutch findings rule out wildlife impact as a primary barrier to adoption, shifting the focus to other obstacles. A closer look at the economics reveals why the Archimedes turbine, despite its engineering strengths, struggles to gain traction in the residential market. The average payback period for a Liam F1 system approaches 22 years compared to just 6 to 8 years for a typical rooftop solar installation. This gap is driven by higher upfront costs and more modest annual energy savings, about $225 per year at current US electricity rates. Beyond finances, regulatory hurdles further complicate adoption. The Liam F1 lacks UL certification, a requirement for most US grid-connected equipment, leaving it in a gray area for permitting and code compliance. Without this listing, no national installer network has formed, placing the burden of integration and maintenance squarely on homeowners. Subscribe for more evidence-driven investigations into overlooked technology. In Seoul's metropolitan suburbs, a series of demonstration homes combined a 5-kilowatt rooftop solar array, a 2-kilowatt Archimedes spiral turbine, and a 10-kilowatt-hour battery. Before the spiral rotor was added, these homes managed about 61% annual energy self-sufficiency, enough to cover most daytime needs, but still reliant on the grid at night or during winter. After integrating the wind turbine, self-sufficiency climbed to over 92%. The spiral's low cut-in speed let it generate during cloudy days, long winter nights, and windier seasons, precisely when solar output dropped. This hybrid approach did not eliminate the grid, but it made year-round, near-total self-reliance possible for the first time in a compact urban setting. Before a single kilowatt can be generated, the homeowner faces a checklist that begins with a wind survey, placing an anemometer at roof height for months to confirm average speeds. Next comes a structural assessment, ensuring the roof can handle dynamic loads from gusts. Installation requires mounting the spiral rotor at least 10 feet above obstructions, wiring a dedicated charge controller, and setting up a battery bank with dump load protection. Routine maintenance means inspecting and lubricating bearings annually, checking the spiral for debris, and testing the emergency brake system. Without a local installer network, every troubleshooting step and safety check falls on the owner, turning a promising technology into a do-it-yourself project with real risks. Subscribe for more evidence-driven investigations into overlooked technology. Today, the Archimedes-inspired turbine stands as proof that technical promise alone cannot guarantee adoption. Economics, regulation, and market inertia still shape what powers our homes. As energy demand grows, the gap between what's possible and what's available matters more than ever. Subscribe for more evidence-driven investigations.